So let's remind the material law. We derive the stress-strain relation with two constants, lambda and g. K. Here, the sigma ij is Kronecker delta plus 2g ij. This is well-known material law. So we are saying this is relation between stress and strain, and material law, same thing, or constitutive model. Let me talk about bulk modulus. Bulk modulus. So when some body is subjected to the hydrostatic pressure, let's say this is hydrostatic pressure. Hydrostatic pressure is applied to the surface of the body. The direction is a normal direction, normal to the surface, right? In this, so hydrostatic pressure minus P is applied. So then P equal minus K B delta V. This body, volume of this body will be changed like this. Okay? So the difference is delta V. And original volume is V. So hydrostatic pressure results in volume change of the body. So pressure increase, so volume decrease. So it means here, so we have a minus here. So this minus pressure means compression. Compression pressure result in the delta V become negative, mean volume is changed in negative direction. It means decreasing of volume. Okay? Here, this is volume variation. And this is K is a bulk modulus. So from this kind of experiment, we can find out the K, right? So all material have a bulk modulus, right? Solid, air, water, okay? Because they're resisting about the pressure. And all the material are compressible, right? So that hydrostatic pressure is same to the mean stress, right? Equal minus P. So let's write down like this. So minus P equal sigma M equal 1 over 3 stress 1, 1, 2, 2, 3, 3, right? This is equal, here let's sum stress, normal stress component 1, 1, 2, 2, 3, 3 using this equation. Then we will have a lambda strain 1, 1, 2, 2, 3 plus 2 over 3G E11 22 33 lambda plus so finally we can have an equation. Here, let's compare this part and this part with this equation. So, K equal lambda plus 2 over 3G. So this is your relation between bulk modulus and lambda and G. And this part become volume change. And P is a hydrostatic pressure. So finally, P become minus K and trace of strain matrix K. And in this equation, lambda equal K minus 2 over 3G, right? So let's put this equation into this material law, okay? Let's put this equation into the material law. Then we can express that material law in terms of K and G. So instead of lambda and G, right? K, Ij plus 2G and this is the result. So this is the same material law, but the material constant is changed. We use the K bulk modulus and modulus G instead of lambda and G, right? Small change, right? But exactly the same equation. And this is the relation between material constant. So this is a very interesting equation because let's look at this part. What's this? Volume change, right? So volume variation. Right? So this will give us tensor, something like that, EKK, EKK, EKK. So EKK is a volume variation. So resulted from the hydrostatic pressure, right? And how about this part? We subtract from the strain. From the strain, we subtract that volume part here, right? So we are saying this is a volumetric strain, and this is a volumetric strain, and this is a deviator strain. Deviate strain. So we can decompose the strain into two parts, volume part and deviator part, as we did for stress, right? Stress has a two part, volume part and deviator part, right? Same. So this volume part corresponds to the hydrostatic pressure. Hydrostatic pressure means volume part of the stress. So volume part of the strain corresponds to the volume part of stress. And deviator part of strain corresponds to the deviator part of stress. Right? So there are relationships, something like that. Okay, so now you know about bulk modulus. And next, shear modulus. So shear modulus gives us relation between shear stress and shear strain. And give us relation between both. So what's the shear stress? Stress Ij. Okay? When I and J is different. If I and J is same, we are saying normal stress, right? So shear stress are positioned off diagonal of the stress tensor, right? Same thing. How about shear strain? Shear strain is the same. When I equal J is different. So from the material law, when I and J is different, for the case J is different, stress Ij is 2G E Ij. Right? You remember? So we are saying G is shear stress. Shear modulus. G is shear modulus. So we can also obtain that shear modulus from the experiments, something like that. Here we have some material, okay, and we give some stress in this direction, in this direction. Then this will deform. There will be own angular deformation, right? So this is H, and you can calculate the angle, right? Angle theta. Strain is a half, shear strain is a half of that angle, right? So we can measure, we know the stress, we can measure strain, then we can calculate shear modulus. Right? So now you know how many constants you know. Lambda, G, and K. Actually, lambda doesn't have important physical meaning, but G and K has a physical meaning. K is physical meaning of volume change, right? And shear modulus have a physical meaning about the angle change, right? So, what kind of the material constant do you know? Which I never mentioned. Young's modulus, right? And Poisson ratio. Both are material constant too. And in engineering, we are most frequently using Young's modulus and Poisson's ratio. Poisson's ratio. How can we get this both ratio, both constant? Which kind of experiment do you need? We need to do just tension test, right? So let's say here, bar here, I like give some tensioning stress somehow, okay? Then, okay, say sigma 1, 1. This bar will stretch it in E1 direction and contract in E2, E3 direction, right? So let's say initial length equal L and additional the L plus delta L. So stress 1, 1 equal E, okay, L over delta L, something like that, right? This is strain 1, 1. So by measuring the length change or this bar, we can calculate the Young's modulus, right? Okay, how about the Poisson ratio here? We need to know about the change in transport direction here. Let's say this is D and D plus delta D. D originally D with, and this is a D minus delta D. So Poisson ratio is defined by delta L over delta D. So here I have a minus, right? You should remember. So this is a Poisson ratio. So from this simple one-dimensional experiment, we can calculate the Poisson ratio. And Poisson ratio can be, Young's modulus can be represented by G and lambda. G lambda plus G, 3 lambda plus 2G. And Poisson ratio equal lambda 2 lambda plus g. This is the relation between lambda g and Young's modulus and Poisson ratio. Okay, so it looks complicated. You can derive this relation from the material law. In the material law, first of all, we need to give a condition. So we have a stress, only stress 1, and strain 1, and other strain and other stress are 0. And then we need to do some manipulation for the, it's a little bit complicated. Then we can find that relation. Also, lambda and g can be represented in terms of Poisson ratio and Young's modulus. And g e to also k equal lambda plus 2 3g equal e. So now we know the material, many material constants. Young's modulus, Poisson ratio, bulk modulus, shear modulus, and lambda, right? 5. But for the linear elastic and isotropic material, we can, if we use only 2 of these 5 constant, we can represent the material law. Okay? So these material laws are changeable, right? So you can use any constant if you want. And there are relations between these 5. So actually, there are some table, something like that. You can find this table from the internet. Okay, so table. There are some table between the material constant. Looks complicated, but yeah, you don't need to memorize. Okay, so here let me give you some note. Young's modulus is always bigger than 0, right? If Young's modulus is negative, what happens? Huh? You pull some material, it's not tensioned, it contracts. It's physically something long, right? Right? So that's not possible. How about the bulk modulus? We put some ball into the water, that it should be contract, but it expands. Then negative k is not possible, right? But G, same. EKG should be bigger than 0, right? And how about the Poisson ratio? So from here relation, you can find the Poisson ratio. Let's look at this. G should be bigger than 0. Then what's the condition for Poisson ratio? Poisson ratio should be smaller than 1, right? No. Bigger than -1, right? Right? And also bulk modulus should be bigger than 0. So 0.5. So Poisson range of Poisson ratio is from -1 to 0.5. So 0.5 maximum. When Poisson ratio become 0.5, what happened? Poisson ratio is 0.5 here in this equation. Then what happened? This part become 0, and it means bulk modulus become infinity. So the meaning of big bulk modulus is no change of volume, because resistance for the volume change is too big. So even you increase the pressure, hydrostatic pressure, volume doesn't change. It means incompressible. So usually one of the assumptions in hydrodynamic for water is incompressible condition. It means for water, the Poisson ratio is almost 0. Not 0, almost 0.5. And yeah, this is little funny, minus Poisson ratio. So you pull this bar in this direction, then physically in the other transpose direction, it should contract, right? But it expands. Yeah, that kind of material we have. So some research found that kind of material. So it's kind of a meta material. So some people like Professor O are interested on this kind of funny material. So, but for usual general engineering material doesn't have negative, okay? So steel have a 0.3, concrete have a maybe 0.2 something, and so most of the material have a positive. But we need to remember negative Poisson ratio is possible, okay? Okay, so in most of commercial software, people like to use Poisson ratio and Young's modulus for as a material property. And one of the very important things is that if we use Young's modulus and Poisson ratio, we can easily represent the inverse of material law. 1 plus, very simply, Ij plus minus mu E K Ij. This is inverse of material law. Here we have strain, here stress, right? Before we have strain, stress in left hand side, strain right hand side, right? This is material law too, right? Inverse rotation. So if we use this, we can make a matrix something like this. 2, 2, 3, 3, 1, 2, 2, 3, 3, 1. With E this is material law using Young's modulus and Poisson ratio. Okay. So in this equation, I didn't put 2 here, right? If we wanted to put 2 here, you need to multiply 1 over 2. Same thing. Okay. So now you know about 3-dimensional general material law. Okay. Okay, now let me think about special case. 2 special case and very widely used special case. And first, plane stress condition. I think you heard about plane stress condition before, right? So let's say there is just some body here, but this body is thin. This is thin body. So, for example, in this case, in G direction, this is thin. And this is a EG, EY, EX. So this body have a EX direction, the dimension dx, and thickness T, and other dimension in y direction is a dy. So this is a thin body. Thin body. So thickness T is much smaller than dx and dy. And loading is applied on the loading. Applied in xy plane. So, for example, loading is applied in xy plane. Something like that. So first, thin body, loading is applied xy plane. So if we have this kind of problem, we can use plane stress condition. It means assumption, this plane stress condition is assumption. So assumption is that traction in EG direction is small, very small, so 0. And this assumption is like this. It means stress Gx is almost 0, Gy, so we are giving the assumption stress about G, Gy, Gg equals 0. This is a assumption we are saying the plane stress condition. So in the plane stress condition, here this is considered to be 0, 3, 3. This 2 is considered to be 0. So we have only considering 2 in plane normal strain and 1 in plane shear strain. Then material law becomes simpler because we don't need to consider 3 stress components. X, Y, and here strain XX, YY, XY, something like that. We can use this simpler material law instead of that complicated 3D material law. Under the assumption of plane stress condition. Okay? So this can be used for thin body. So plate and shell and beam are usually very thin. Okay? So we can use this material law. And here we need to note, in this case, strain Gx, strain Gy is 0, but strain Gg is not 0 in general. Due to the Poisson effect, we can have a strain in thickness direction. But we don't need to consider. But if we want, we can calculate this strain. And next is a plane strain condition. So case is a little bit different. So body is not thin, very thick. Length of the body is almost infinity. So let's say this is a EX, EY, and EG. So this is a DX, DY. So we are using plane strain condition for long prismatic body. Prismatic means section doesn't change about the here g-axis. Same section for long prismatic box. So length of this body is much bigger than dimension of cross section x, d, y. And also loading is applied in xy plane here. Very similar case, but one is a thin section, the other one is a very long section. So long body, very thick body, very thin body, two extreme case. In this case, assumption is that no gradient in UG, displacement in G direction, UG, and UG equals 0. So if you take the differentiation about G, about displacement in G direction is 0, and also displacement in this direction is 0. Okay, so there is no displacement in this direction. And this condition results in strain component Gx about Gy and Gg equals 0. So plane stress condition and plane strain condition is very similar. Plane strain condition, plane stress condition, stress about G is 0. Plane strain condition, strain about G is 0. So both are similar, are totally different. Okay? Okay, in this case, we are using also different material law, XX, YY, XY. Okay, E1 minus 1 plus lambda 1 and here we need to have 3 strain. Strain XX, strain YY, strain XG. So similarly, I need to note strain GX, GY equals 0, but stress GG is not 0 actually, due to the Poisson effect. Okay, so we can use the plane strain condition for the analysis of very long structure like a dam and breakwater. Okay.